In this video, we're going to take a look at the inner workings of the venerable 555 timer IC. This is a block diagram of its innards. As you can see, there's not an awful lot to it, but it's very clever and elegant in its design. The first part we come to is a voltage divider, which provides reference voltages at 2/3 and 1/3 of the supply voltage. The three resistors are 5k each, and some have speculated that that's where the 555 number came from, but the designers say it's just coincidence that 555 was the next number that was available. Next we come to two comparators, which compare those reference voltages with two inputs, a threshold and a trigger input. The upper comparator goes high if the threshold value exceeds the 2/3 of the supply voltage reference, and the lower comparator goes high if the trigger input drops below the 1/3 reference. The outputs from the comparators feed into the R and S inputs of an RS latch. If you're not familiar with what an RS latch does, I'll point you towards Ben Eater's excellent video on the topic. I'll put a link to it in the notes down below. But basically, when the S input goes high, the output of the latch goes high. When the R input goes high, the output of the latch goes low. And when both are low, then the latch just stays as it was. Finally, then there's a transistor. The base of the transistor is connected to the inverted output of the SR latch, the Q bar output, and the collector is presented to the discharge pin in the IC. We'll see how that's used in just a moment. The Q output from the SR latch is buffered and presented as the output then from the IC. And that's really all there is to it. What we have here is the standard Astable configuration for a 555 timer. It produces a square wave at its output pin, the frequency and duty cycle of which depend on the two resistors and the capacitor on the left hand side. The capacitor charges through one of the resistors, the 100k one in this case, and then discharges to the two through the discharge pin on the IC and that transistor we mentioned earlier. The voltage across the capacitor winds up in a triangle wave varying between 1 and 2/3 of the supply voltage, and that can be useful sometimes too. Okay, let's have a look at a simulation of the Astable oscillator in action. When power is applied, the voltage across the capacitor begins to climb. It climbs until it hits 2/3 of the supply, at which point the top comparator goes high and hits the reset input to the SR latch. That causes the output of the SR latch to go low, which turns off the output to the IC and turns on the discharge transistor. That begins the process of discharging the timing capacitor. The capacitor discharges through the discharge pin and that transistor until eventually its voltage drops to 1/3 of the supply. At that point, the lower of the two comparators goes high and strobes the S input to the SR latch. That causes the output of the SR latch to go high, turns off the discharge transistor, and the cycle starts all over again. Notice how brief the pulses out of the comparators that drive the S and R inputs to the SR flip-flop are. Okay, what we have here is an implementation of the 555 timer circuit along with some instrumentation just to allow us to sort of visualize what's going on inside. This portion of the circuit is the actual implementation of the 555 circuit. The chip on the left is a dual comparator, and the chip on the right is a quad 2-input NAND gate from which the SR latch is built. Again, I'll refer you to Ben Eater's excellent video about the SR latch for more detail about that. The transistor, the discharge transistor, is just there behind the yellow LED, the center of the screen, and the blue LED shows the state of the output. The rest of it then is just an instrumentation to let us have a view of what's going on inside the IC. The left-hand part of the board is actually mostly pulse stretchers, so that it stretches those set and reset pulses. They really are very, very short, so in order to be able to see them on LEDs, the pulses need to be stretched a bit just to make the LEDs light for long enough. And then of course there's the voltmeter at the back that just shows the voltage across the capacitor. The little small breadboard at the top is just an op-amp buffer to buffer the voltage coming out of the timing capacitor before it gets fed to the meter. Okay, let's see what happens when we apply power. I'm powering it with 5 volts, and you can clearly see the voltage alternating between about 3.3 and 1.6 volts. When it hits the thresholds, then the set and reset pulses are there, and you can see the discharge light coming on. Here, just slow down a bit. The oscilloscope trace up in the top right corner shows the voltage across the capacitor, and also the set pulses. I'm actually showing the stretched set pulses at this time base. The unstretched ones are barely visible at all. That's it. If you enjoyed the video, please click like and feel free to leave a comment. Bye.